Good evening to all. Today we are going to discuss about very important thermodynamic process that is called isentropic process for ideal gas. So I hope this video is going to be very interesting. So please do keep watching until the end and don't forget to subscribe my channel and hit the bell icon. Thank you. So let's begin the discussion for thermodynamic process for isentropic process. And before that, let's understand some basic information about thermodynamic system. If people say thermodynamic system means it is related to gas, and gas can be air or any hydrocarbon. It is nothing related, it has no relation with compressor, it is no relation with expander or turbine. If you call the thermodynamic system, that means it is focal point is the gas, that is uh, so people say thermodynamic system means it is a gas. So with that point of consideration, there is some, what is called real guideline that what are the sign convention for these thermodynamic system. If heat is added to the thermodynamic system, it is considered positive. If heat is removed, it is considered negative. Similarly, work is done by the system, it is considered positive. When work done on the system is negative. When the energy level increases, it is considered positive. When energy level of the system decreases, it is considered negative. These are the sign convention. Types of thermodynamic system, it is open system, closed system, and isolated system. In case of open system, mass transfer occurs, energy transfer occurs. In case of closed system, when mass transfer doesn't occur, only energy transfer occurs. In case of isolated system, neither mass transfer nor the energy transfer occurs. Ideal gas equation of state PV is equal to nRUT. So on simplification, we can write P small v RT, with P is a pressure, V is a specific volume, R is a gas constant, and T is the temperature. Work transfer for the closed system, it is written as integration of P dV. In case of open system, it is written as minus VdP, and for the closed system, it is area under the curve on x-axis. For the open system, it is area under the curve on y-axis. Work done by the system is positive, work done on the system is negative, and work transfer per unit mass is called the work height. Energy transfer for the closed system is equal to the internal energy change. So which is written as energy transfer for closed system is integration of CV dt. Energy transfer for the open system is equal to enthalpy change. So energy transfer for the open system is equal to integration of Cp dt. In energy of system increases is positive, energy of system decreases is called negative or considered negative. As for first law of thermodynamics, the heat transfer is equal to work transfer plus energy transfer, which Q is equal to W plus E. But very important information is the first law of thermodynamics assumes efficiency of thermodynamic machines is 100%, means there is no losses during the transfer of work, energy, and or heat. So efficiency of machine is 100% for the first law of thermodynamics. Isentropic process for the ideal gas, we can see on PV diagram 1 and 2 is a compression process. Here 1 and 2 here is expansion process. This is on TS diagram, constant entropy remains constant 1 and 2, and this is 1 and 2. So when compressor occurs, pressure increases, temperature increases. When expansion occurs, pressure and temperature both decreases. But there is no heat transfer in the isentropic processes, and so entropy remains constant. So work transfer is equal to energy transfer as per the first law of thermodynamics. Isentropic process in the closed system, you can see on PV diagram, area under the curve. On x-axis is the work transfer, which can be derived as below. Work transfer for the constant entropy process, S is constant, and we have formula PV to the power K is a Cp by Cv, is C, that is constant, so we can write P is equal to C into V to the power um, minus K. So P1 V1 K is equal to C is equal to P2 V2 power K. V2 by V1 is equal to P2 by P1 to the power minus 1 by K. Ideal gas equation state PV is equal to RT, P1 B1 RT1, P2 B2 RT2, T2 by T1 is equal to P2 by P1 to the power K minus 1 upon K. Ideal gas equation Cp minus Cv is equal to R, so K is equal to Cp by Cv. So work transfer, W is equal to P underscore dV, sorry, integration of P into dV. So after replacing P, we can write integration of C into V to the power minus K dV. So further integration, we simplify, write that. We can simply write W is equal to K R upon K minus 1 into T1 minus T2 after simplification. Or this can be also written in this form. W is equal to R upon K minus 1 into T1 bracket start 1 minus P2 by P1 to the power K minus 1 upon K. So work transfer per unit mass W is equal to R upon K minus 1 into T1 minus T2, and total work transfer M is equal to W is equal to M into R upon K minus 1 into T1 minus T2. This is the work transfer, and on PV diagram you can see area under the curve on x-axis. And energy transfer for the constant Cv dt, we can write Cv into T2 minus T1, so we can write as per first law of thermodynamics, heat transfer W plus E. So we can write Q is equal to this plus this. So on temperature form, we can write Q is equal to Cv minus R upon K minus 1 bracket close into T2 minus T1. So heat transfer per unit mass Q is equal to Cv minus R upon K minus 1 bracket close into T2 minus T1. For total, you have to multiply mass. On PVTS diagram, you can see the entropy remains constant, and heat transfer on this curve is 0. So heat transfer on this process is 0. So in heat, because it is isentropic process. Now the entropy change, if you see, just Q has written like in this form Cv into R upon K minus 1 into T2 minus T1, and just dividing by, we can write in dt form. So we can write Q is equal to Cv minus dt, Cv minus R upon K minus 1 into dt. So S will be divided by T. So dt integration, on integration we can get Cv into Cv minus R upon K minus 1 into ln means log T2 by T1. So this is entropy change. For this, for total entropy change, just multiply with mass, and on TS diagram this is entropy change, but entropy change is 0. That means because entropy is constant here. Now isentropic process in open system. Area under the curve on PV diagram y-axis will be give the work done for open system. So entropy remain constant. PV to the power K is equal to constant. So V will be, sorry, V is equal to C to the power 1 by K into P to the 1 by K, and P1 B1 power K is equal to C P2 V power K, V2 by V1 is equal to P2 by P1 to the power minus 1 by K. PV is equal to RT1 P1 V1 RT1 P2 V2 RT2 T2 by T1 is P2 by P1 upon K minus 1 upon K. Cp minus Cv is equal to R, K is equal to Cp by Cu. So work done will is equal to minus VdP. So after putting all the details, you can get W is equal to R into K upon K minus 1 into T1 bracket start 1 minus P2 by P1 to the power K minus 1 upon K. And in temperature form can be also written W is equal to RK upon K minus 1 into T1 minus T2. So this is work transfer W RK upon K minus 1 into T1 minus T2, and total work transfer just multiply with mass, and this is shown on the PV diagram for the work. Now entropy change, sorry, energy transfer, energy CPDT, we can write CP T2 minus T1. So heat transfer is a work plus energy transfer. So Q is equal to W, sorry, this W is not required. Q is equal to this plus Cp T2 minus T1. So we can write Q is equal to Cp minus K R into K upon K minus 1 bracket close T2 minus T1. So this is the heat transfer per unit mass. Q is equal to Cp minus R K upon K minus 1 into T2 minus T1. So total heat transfer just multiply with mass, but here you can see the area on the x-axis is 0. That means for isentropic process heat transfer is 0. Now entropy change just S is equal to Q by T. So Q we know this form, just dt form can be written in this form. So S will be divided by T. So this into log, that is ln T2 by T1. So this is entropy change. For total entropy change just multiply with mass. On TS diagram it is clear that entropy change is 0. So because entropy is a constant here. Now let us understand with an example. So nitrogen gas has initial pressure and temperature of 0.5 bar gauge, 30 degrees Celsius respectively. Gas is compressed such that the final pressure reaches to 0.8 bar gauge on constant entropy process with consideration of ideal gas. Calculate work, heat, energy transfer and entropy change during this process for considering closed and open system. Also calculate inlet and outlet specific volume. Following data are given: mole weight of nitrogen 28, universal gas constant 8314.5, specific heat capacity at constant volume 20.86, local barometric pressure 1 bar absolute. So isentropic process in closed system, local pressure, temperature. So in convert inlet pressure P1 is equal to gauge plus atmospheric pressure, that is 1.5, inlet temperature 30 degree, outlet pressure 1.8, mole weight is 28, specific CV is given, RU is given. Now our gas constant is this, Cp is given, Cv is given, is converted Cv into 1000 upon m, that is multiply 1000 for joule, divide m to joule per kg. Once then Cp is R, Cv plus R, which is given, K is Cp by Cv is known, V1 is calculated, V2 is calculated, T2 is also calculated, then work done is calculated, which is minus 12,045, and internal transfer energy transfer Ce is equal to Cv into T2 minus T1, which is 12,005. So heat transfer is 0, entropy change is 0. Now for the open system, work transfer is minus 16,846 using this equation. Energy transfer is same, plus 16846. So heat transfer is 0, entropy transfer is 0. So I hope you have enjoyed the thermodynamic power process for isentropic system, isentropic process for thermodynamic system for ideal gas. So thank you for watching.